Hello everyone, I'm Fuyuan from Nanjing University of Aeronautics and Astronautics. The content of my speech today is power allocation schemes for submarine maximization of uplink massive MIMO system with maximal ratio combined. There are 5 parts in total, which are introduction, system module, and channel module. Problem formulation, simulation results, and conclusion. First of all, for massive MIMO systems, there are many issues worthy of study, including hardware damage, backhaul capacity limitations, IS, LOMA, and physical layer security. The motivation of our work is to propose power allocation schemes for submarine maximization of uplink massive MIMO system under the rate constraints, which is worthy study in the existing wireless communication system. The goal of the paper is to investigate the performance of our power allocation schemes with imperfect channel state information in uplink massive MIMO system. The challenge of the paper is transforming the non-convex and non-concave submarine optimization problem into a concave problem. Next, I will introduce the system module and the channel module of this paper. This paper considers a connected single cell, where there are key users in the cell. The base station is equipped with N antennas, and incomplete channel information is also considered. At the receiver, the base station uses MRC method for single signal detection. Like many papers, the base station obtains the channel state information through uplink trailing. After uplink trailing, we can get the estimated channel as shown in equation 1. According to MRC method, the received signal of case user is written as equation 2. With the above analysis, we can obtain the case user's rate as shown by equation 3. We deduce the achievable rate of user K in the front, and then we should study the system rate maximization problem of the uplink massive MIMO system. In this part, we will give the power allocation schemes that maximize the system rate, which are near optimal and suboptimal power allocation schemes, respectively. First, we give the derivation process of the near optimal power allocation scheme. We establish an optimization problem for maximizing the system rate, as expressed in equation 4. We can see that this optimization problem with respect to pK is a non-convex and a non-concave problem. According to the optimization methods of the concave-convex procedure, we will turn this problem into a concave problem later to find a power allocation scheme. To begin with, we transform the minimal rate constraints into equation 5 and 6. The reason for this is to turn the rate constraints into a convex state. According to the equation 5, and 6. We define the upper and lower bounds of the transmit power Pk of the user K as equation 7. After the constraints are transformed into convex sets, in order to obtain the near optimal power allocation scheme, we only need to transform the optimization problem into a concave one. Here, we take the concave convex procedure method to solve the optimization problem. Namely, the transformation of objective function in equation 4 with CCCP method is derived as equation 8. Based on the first-order Tanner expansion, the maximization problem 4 can be transformed into equation 9. With above analysis, the optimization problem is transformed into a concave one. Then, CVX software can be used to get the optimal value of subrate. We take the performance obtained by CVX as a benchmark. Next, we continue to derive the near optimal power allocation scheme. The derivative of equation 9 with respect to Pk is shown as equation 10, with equation 7 and 10. We can get the near optimal power allocation scheme of case user as shown as equation 11. In order to understand the near optimal power allocation scheme more intuitive, we give the steps of the near optimal power allocation algorithm. We have already given the near optimal scheme before, which is related to small scale and large scale feeding information, and requires CSI feedback frequently. Therefore, a suboptimal PA scheme only depending on the large-scale feeding information is developed. The difference from the near-optimal power allocation scheme is that the latter doesn't require frequent channel state information feedback, which means a lower complexity of suboptimal schemes. We consider the case of N is very large for uplink massive MIMO system. An approximate expression of the objective function in problem 4 is shown as equation 12. With a similar CCCP transformation process as near optimal scheme, we can get the approximate sum rate optimization problem as equation 13. Based on the BCD method, the suboptimal power allocation scheme of the user key for the problem 4 is shown as equation 14. Similarly, the optimal solution of a suboptimal power allocation scheme can be obtained by algorithm 1. The following part is a performance comparison of the two allocation schemes. We take the performance of CVX as a benchmark. Firstly, we give the simulation parameters as table 1. Next, we give a summary comparison for different uplink training coefficient tau and maximal power Pmax. It can be seen that the sum rate obtained by near optimal power allocation scheme always perfectly match that offered by benchmark schemes as n increases. Meanwhile, the sum rate gap between the near optimal power allocation scheme and the suboptimal power allocation scheme gradually decreases as n increases. And the two schemes have similar performance of n is 60 dB. As Pmax increases, sum rate increases. Meanwhile, sum rate increases as tau decreases. Finally, we give the sum rate comparison for different rate constraints, we can see that sum rate decreases as Rmin increases. With higher rate constraints, the number of channels that don't meet the rate constraints will increase. In the simulations, we set the value of sum rate under these field channels to 0, which leads to the higher rate constraints, the lower sum rate. At last, I will summarize the paper. This paper gives power allocation schemes of sum rate maximization in uplink massive MIMO system under rate constraints. The difference from current research is that future research will mainly involve distributed massive MIMO and cell-free. That's all my presentation. Thank you.